Hello class. In this lesson we'll be learning the definition of a point of concurrency and how we can locate them in triangles. So to start off, we have this triangle and we want to draw all the perpendicular bisectors of the sides that we can. So I'll demo one of them for you, and the steps are the same for the other two sides, and then I'll show you the final product. So you take the endpoint, and it's the same construction as before. You're just picking one segment and ignoring the others. Take the pivot, put it on one endpoint, open it up to the other endpoints. Draw a circle, and like we learned, you don't have to do a full circle. As long as you have the arcs in the places where they're going to intersect, that's fine. And without changing how large it is, draw another one. And if I zoom out here, we should be able to see the 2 points of intersection. So now we're going to connect those with a line to make our perpendicular bisector. So there we go. There's one of them. And now you're going to repeat this process for the other two. So if you're doing this on a piece of paper, you want to draw your circles kind of light because you're going to have at least six circles or at least arcs from them on your paper. So it can get a little bit messy. So here is the final product. And what do you notice about them, actually? Well, they all cross at the same points. And this point has a special name. It is a type of point of concurrency. And it is called, well, we'll get to what it's called in a sec. First, when we have three or more lines crossing in one spot, one point, that's called they're concurrent. Any two lines that aren't parallel will always cross one time. But putting a third one there isn't always, third one's not always going to pass through it. And that point is called the point of concurrency. And so there's actually 4 different types of concurrency. We're going to learn about 2 of them in this lesson. The one from the perpendicular bisectors is actually called the circumcenter. And that comes from the same root as the word circumference. So we'll get to the reasons as to why this one's called the circumcenter later in the lesson. But it has to do with circles. And so here's an example of a different triangle with a different circumcenter. And if you notice, this one has the circumcenter on the inside, while in our previous example, it was on the outside. The circumcenter could also be located on a triangle. So those are 3 different possibilities. So now the question is, how do we know that the circumcenter will always exist? How do we know that these perpendicular bisectors, all 3 of them, will always cross at one point? So to do that, we're going to use the property of perpendicular bisectors we learned in the previous lesson. We know that any point on the perpendicular bisector is equidistant from the 2 endpoints of the segment. So P is equidistant from A and B because it's on its perpendicular bisector. And so if we look at that, we know that this distance in red from P to A and P to B must be the same. I'm a little bit off. And we know the same thing for B and C. P is equidistant from B and C because it is on its perpendicular bisector. So now, by transitivity, this one's equal to this one. So, I'm sorry, let me say it like this. The first segment here is same length as the second segment. We know the second segment is the same length as the third one. So the first and the third must have the same length. And so P must be equidistant from A and C because those distances are all the same. So since it's equidistant, it must be on its perpendicular bisector. So that's a point of concurrency. So we know it lies on 2 perpendicular bisectors and it must lie on the third one. That's what we're getting at. Okay, now we're going to look at our second point of concurrency. This one is called the incenter. In has to do with the fact that it's always inside. And more specifically, I'll show you with circles what incenter more specifically means. But the way we make it is that we do angle bisectors. So now we want to bisect each angle here. I'll demo one, and then I'll show you the final product. So pick a vertex, draw a circle, go to one point of intersection and put the pencil on the other point of intersection that we have. Draw a circle there. Go to the other point of intersection without changing how big your compass is. Draw that circle. And then if we connect our corresponding vertex to that point, we have an angle bisector. So I'm going to repeat that for the other two vertices. And here's our final product. Here's our incenter right in the middle. So that's also a point of concurrency. And here's a different triangle, and there is its incenter, Q. And so now in 2 steps, we want to say how we actually made the incenter. So what was the first thing we did? We bisected each angle. And then what did we do? We labeled where all 3 crossed as Q. So how can we be sure that the incenter is always going to be that point of concurrency, that they're always going to have the 3 angle bisectors crossing it? We're going to do a similar argument that we did before. Now, since Q, the incenter, is on the angle bisector, it must be equidistant from the 2 sides of the angle because it cuts it in half. And when we say distance from the sides of the angle, we mean the perpendicular distance. So for example, we know that point Q is equidistant from both AB and BC. So this looks like it lines up with that angle bisector. That's not always going to be the case. So these in red are going to be perpendicular. I'll draw those little squares in there. Okay, so these distances are red, are going to be congruent. Now we can do the same argument since we know that we have an angle bisector over here for angle C. We know that this segment that I'll put in blue, this must be equidistant from, Q is equidistant from AC and BC as well. So we know that the second one and the third one are congruent. So by transitivity, you know that the first and third segments are congruent. So Q must be on the angle bisector of angle A. So here's that argument written out for you. So we know that when we have a triangle, we can always get that point of concurrency by using either the perpendicular bisectors or angle bisectors. So you'll get a different point of concurrency based on the type of construction you do. So here is the reason why we call it a circumcenter and an incenter. If you notice, the circumcenter is in the first picture. And if you draw a circle using the circumcenter in any point on the triangle, that circle will touch all 3 vertices, and it's on the outside. So we say that the triangle has been circumscribed. When we look at the incenter, we know that all those. Let me go back to circumcenter for a second. So if you look here, if we connect A to L, that's a radius. A to K, that's a radius, and A to J, that's a radius. So there's a circle. If we look at the incenter now, we can draw a circle that's inscribed inside the triangle, so it touches each side exactly once. And if we draw those radii in, draw them in blue, it should look like this. So that's why we call it the circumcenter and the incenter. Here we have a circumscribed circle, and here we have an inscribed circle. And using the facts, spoiler, using the facts we just learned, how can we find the center of a circle if we don't know where the center is? So it's going to have to do with triangles, and it looks like it's a little bit tricky to draw that triangle around a circle. So let's stick to using the circumcenter. So how do we find this point A, which will be the center of the circle, and the circumcenter? Well, we need a triangle, right? So inscribe a triangle in a circle, and then use perpendicular bisectors to find the circumcenter. So you can do this process over here to find its center. So in this lesson, we learned what points of concurrency are and how to find them. Thank you for watching this video.